and I have single agent versus multiple agents. So a single agent, your computer program is the only thing in the world. There is nothing beyond it. Your program is the only thing. Classic examples. I let a robot go at a mine location. It's the only one in the mine location. There's no one. Like if I pace around at this mini recording studio of mine, I'm the only one. Whatever happens, I'll do it. Unless there's a ghost, the possibility of which is extremely small. So, it's single agent. Multiple agents, there are many of you, and all of you are physically acting in exactly the same world. So, many people, one physical world. So, you are doing something, somebody else is doing something else. So, remember the morning breakfast fights. You want that piece of stuffed bread, but your friend is also there. Both of you pounce on it. One of you will get it. Single agent, so simple. Pick it up. Multiple agents you need to fight. Now all of a sudden, single agent, long drive, wonderful road, just travel around. Multiple agents, traffic jams, you need to account for it. Congestions, overtake that bad guy, somebody bumps on your favorite car, bad for you. Multiple agents, robots in warehouses, multiple agents. So, if there are multiple agents that are simultaneously doing something in the environment, we denote it like this. So that is your environment. And these are agent 1, agent 2, agent 3, agent 4, agent 5. And what each one of the agents does is that it takes reading from the sensor and gives it back to the environment. So that sensor for agent 1, that's actuator for agent 1. This is sensor for agent 2, and this is actuator for agent 2. This is sensor for agent 3, and this is actuator for agent 3. That's sensor for agent 4 and actuator for agent 4. And of course, you've got exactly the same thing around over here. So that's how we model it. So this little thing is what is the environment, and all the others are what are the agents. Now, multiple agent systems are again classified into two varieties. The agents are sometimes cooperative, and sometimes the agents are competitive. So, cooperative. When you all cheat in examinations, now they are online, everybody gets very good marks. Cooperation. So, one guy solves question 1, one guy solves question 2, one guy solves question 3, you share the solutions, and everybody gets marks for all 3 questions. Cooperative. You play FIFA as a team. Within the team, you are cooperative. The way that we faculty act, cooperative. Each one has the common goal of making your life a hell, and we play as a team. So sometimes I'll take extra class, sometimes Professor Nandi will take extra class. Cooperation as a team. Competitive, you act opposite of each other. So, examinations, assessment, my motive is to give as difficult paper as possible so that everybody gets bad marks and I have little copies to correct. Imagine a bundle of 200 copies, you cannot even sleep. Give difficult question paper, nothing to evaluate. Your aim is to write as much as possible, score as much as possible, competitive. Cricket match, India versus Australia, competitive. Driving is interesting where you see both cooperative and competitive behavior simultaneously. So, and I like this example as well. So that's a little road, that is your vehicle, you are going here, probably with your family on an outing, and unfortunately for you, is a girl who is driving this vehicle and will just not allow you to overtake. Competitive, you'll try zigzag, left, right, everything. Of course, eventually the vehicle going here will clear and you will overtake, but there's a limited resource. You're sharing it. Competitive. Sometimes what will happen is something which is a bit different. So the same road, you are traveling around over here and you've got the same girl traveling around over here. For no reason, the girl will get aside. Why? Isn't the girl intelligent? Doesn't she know that drifting towards the side is gonna increase her time, reduce her speed, and increase her distance? The girl is intelligent because she and you are playing as a team. Her act of cooperation is the one that helps you, and she's not maximizing her own objective, she's also maximizing your objective simultaneously, cooperative. So when you cheat in homeworks, that's what happens. The topper who shows the answer is wasting time, but a little help from him does make you get good marks. Now, I teach this thing to very senior students as well, and believe me, if I just give you random examples, you will not be able to classify systems as either cooperative or competitive. So, only for the sake of completeness, I'll give you the pure definition. You like it, take it. You don't like it, come back after the entire course and look at it again. A system is competitive when the two agents have opposite objective or performance measure. Your win is his loss, his win is your loss. That's why if a company says in campus recruitment, whatever, we have only one seat, all the brotherhood, sisterhood, friendhood goes into the dustbin. If you help your friend, he takes the seat, you're gone. So it's competitive if the objectives are equal and opposite. So if other wins, you definitely lose, and you don't want to do that. It's cooperative if both the agents have exactly the same performance measure, and I'm not talking about reducing distance. I'm saying reducing the sum of each other's distance, reducing the sum of each other's travel time. Then it's purely cooperative. And that's exactly what happens in assessment in a homework style. So your aim is everybody gets very good marks. Now we don't have constraints that everybody will not pass. Everybody can pass. So everybody has the same objective. Let everybody score very good and everybody pass the assessments. Wonderful. So then that's cooperative, and that's exactly what you do as sports. Did ever a player complain that if you keep me on bench, what will happen? The player is intelligent. He's not playing for himself. His objective measure, his performance measure, I keep highlighting performance measure is the most important thing in AI. There are disasters, including my own work, where solving for the wrong performance measure led to a chaos. So, the player is not playing for himself, the player is playing for the team. Somebody is better, performs well, everybody share the credit, and he's happy. So that's what is cooperative and purely cooperative. Now, in every example that I took, you'll see that there was always a sense of competition and always a sense of cooperative, because you never had exactly the same objective measure, performance measure for everybody, nor was every time the performance measure equal and opposite. So just like every solution, I've left at a kind of a dilemma. That's exactly what I do here as well. Now, there is another classification that is very important for us in a multi-agent system. And so the previous one was on the basis of the number of agents. Now it's on the basis of communication. So the agents can either have no direct communication, or the agents can have a direct communication. So, okay, there is not really something which is no communication. Just like I said, there is nothing which is non-observable. So it's no direct communication when the agents cannot talk to each other, but they can observe each other's effects. So you're cheating in assessments. The instructor is right ahead of you. You cannot say, hey bro, show me the answers of question number 1, 3, and 5. Give me those pages. I'll copy and I'll return. No direct communication. But you could make in small gestures which will be understood by the person in front, and you know how he'll show you. Online examinations, you would just call up your friends and stay on a conference, discuss the answer, a direct communication. So because we're talking about software, a direct communication is when the agents are connected by a Wi-Fi, LAN, Bluetooth, and any protocol that you know of. And they have standard protocols. It's no direct communication when they can see each other, hear each other, smell each other. They are olfaction sensors. I'm not just making that up, believe me. And similarly others. So you don't know where the other agent is. You could have an estimate based on what you see. You don't know whether the agent in front is, what is that guy doing? However, you could actually see what is he doing and adjust accordingly. So let's take in a classic example about how communication really helps. So this is not far away from here. This is where I am sitting, and after that, using this route, I'll go out. And of course, you know that there is a door over here that helps us keep cool. You really need it. Allahabad is extremely hot these days. And I make my way around over here. And of course, there is Professor Nandi, who is just parked his car and is coming around over here. So this is me and this is Professor Nandi. Now, a lot of things could happen. The one thing which could happen is I move, he moves, and we say, oh, we both move at the same time. I step back, he steps back, we say, oh, we step that at the same time. So I move and he moves. Or what will practically happen is that if we have a direct communication, I will just shout out, you first. So, games, volleyball, mine. Cricket, mine, when you have to take a catch. Taking a single shout out, one, two. So that's how direct communication helps. Now imagine the same problem in the case of robots. It becomes absolutely simple. So if I was a robot and Professor Nandi was also a robot and we were here, we'll pre-calculate that, okay, both of us will come at the same time around over here, and much before we even get to this bad situation, much before we get into this extremely bad situation, what will happen is that we will discuss, interchange messages and sort that out and make a plan beforehand. So of course, Professor Nandi has a higher priority. He is an old man and he works faster than me. That's a secret. He works much faster than me. I cannot catch him up. So he'll come like this, and what I'll do up is, my robot, what it'll do up is, it knows that Professor Nandi would be here, so there's no point in taking this route. I'll slowly get around over here. That's only possible if you have a communication which is in between. Now, by the way, I did introduce that up. This problem is a classic AI problem, and the solution is what is called as the randomization. It says many times for situations like this, your actions need to have a random element. And that is one of the most important things in AI, that sometimes you really need to act randomness. You people have studied operating system and all that, so you know that when you continuously book and unreserved resources, what happens. So you add a random element, and that is what really makes in some kind of a trick, some kind of a tiebreaker, and sometimes of something that will really help you around. So now we've discussed more of the background, and I can come to the more important issues. But before that, I will leave you with two important notes. Number one is the fact that if I say that there is an intelligent agent, so let's say there is an AI agent, and the AI agent just went to the kitchen to see if your mom was there or not. Now, it may look weird. You are taking actions for nothing. Is that intelligent? A similar example will be that in the physical examinations, most of the students go to the washroom just to check if their friend is there or not. So this is called as exploration. Exploration means that you are gathering information. And remember, in AI, sometimes you need to take actions not because of the fact that the actions perform some physically important thing, but sometimes you have to take in actions that eventually lead to you having more information. Why are we spending so much on random vaccines? Most of them are not going to work. We are gathering information about the disease. It's information gathering, it's exploration. And so we talk about partially observable system. Many times you may need information, it may not be there. So all that you do is that you take actions which gather that information. The second thing that, of course, I will leave you with is the fact, why did I have this classification? So a simple reason is every algorithm will have assumptions as either of these. Some only work for static, some only work for dynamic, some only work for deterministic, some work for stochastic, some work for fully observable, some work for partially observable, some work for single agent, some work for for multi-agent. So that's also one of my wonderful PhD problem, bad design that I learned very quickly. Model the multi-agent problem as single agent, terrible results, absolutely failed, and learned that the hard way that be very careful when you invest on an algorithm. Poor assumption leads to something which does not have good results. So an obvious thing that will come to your mind is partially observable is more generic to fully observable, stochastic is more generic to deterministic, sequential to episodic, dynamic to static. Assume everything moves. It doesn't move, your algorithm will still do it. Continuous is more generic to discrete, multi-agent is more generic to single agent, and similarly with all others. Now, why don't I always assume this? Why do I ever assume this? And the answers are two. Number one, that sometimes this category is a lot more computationally expensive as this category. So you invest a lot of time. You will not have that time, to be honest. Like there have been AI systems that predict weather, the only problem is prediction of one day's weather takes 3 days. So rather than waiting for the output, you can go outside and check the weather by your bare naked eyes. Bad AI system. Sometimes you make in stock market prediction systems. The only problem is your prediction for the next 3 seconds takes in 5 seconds. Rather than waiting for 5 seconds, rather than investing 5 seconds on the algorithm, wait for 3 seconds, look at it yourself. Many times, when I say that I just need to go home, it's static. What will happen? The only problem is I wait for too long a time. IIIT has constructed new roads. So there are hard time constraints. It's a real life system. You cannot afford more time than what the system allows you. So you may not be in a position to take this. You may only have to take this route. Sometimes it's weird. If you assume this, your performance will be low. If you assume this, your performance will be better. Remember, when I say computational rationality, it is not only making the best expected decision, but it is making the best expected decisions, which we already studied, with additional constraints, and the additional constraints can of course be your limited knowledge. So I say given limited knowledge, given limited compute, given limited memory, given noisy sensors. So with all these assumptions you need to make it. So if you observe it from this school, it might sound a lot more interesting. It's generic. But your performance may not be that good as you compare to this school, and therefore you really need to understand at what level of abstraction should my problem be solved. Should it be solved at the highest level of abstraction? Should it be solved at a lowest level of abstraction? Or what most of my work is, we need hybrid algorithms, we need hybrid AI algorithms which work at multiple layers of abstraction and make you do exactly what you want, and that makes in a complete AI based system.